Hi, thank you for watching this video about object swelling motion planning for dual arm robot using empty space images. This was presented in IAS 19 in Genova. Okay, this picture shows a dual arm robot next stage equipped with an RGB camera on top. Using this camera, RGB images are used as input and hand positions are determined as motion outputs. So we have so far proposed a motion planner based on CNN and Moscow CNN. And this motion planner was trained through motion instruction and imitation learning. This figure shows the motion planner based on the CNN, and as you can see here, segmentation images are used as input, and in addition, goal directions in the images and the current hand positions are also used as input. And these are the motion output determined by this motion planner. So the robot based on this motion planner succeeded in storing the object into the empty space provided by the partitions in the shelf. Okay, however, if a shelf has no partitions, um, the space is divided by the placed objects. In such cases, some spaces may not be sufficient for storing additional objects depending on the placed ones. So here, let us first define the space which is sufficient for object storage as the empty space. Here, let me show you an example. Now, in this picture, an object is placed in the shelf. Because both spaces are sufficient for object storage, this shelf has two empty spaces. On the other hand, even when shelves contain similarly placed objects, these camera images might be appear almost identical. However, the slight differences in object placement sometimes change the empty spaces. Actually, compared to the left, the object in the line is a little bit shifted to rightward. So in this case, in the left, only the line space is empty, and in the right, both the left and right spaces are empty. So these are indicating that it is pretty much hard to identify correct empty spaces based only on these visually similar image inputs. So this is the challenge of this research work, which is visual spatial perception. Okay, for this challenge, we present an empty space classifier based on CNN, and this is the architecture of this classifier. First off, segmentation images are used as input, and in the output, let me only focus on the empty spaces for both hands, which are represented by n+1 neurons. This is because that when n objects are placed in the shelf, the space is divided into n+1. And the empty space K is represented by a one hot vector where a value of 1 is assigned to an empty space. Here, let me explain an example. For example, now an object is placed in the shelf, meaning n equals 1. So the empty space is classified as either 1, 0 or 0, 1. Here, 1, 0 indicates that the object is placed in the left empty space to the placed object, and 01 indicates the object is the empty space is on the right side of the placed object. And this classifier is trained using supervised learning applied to the CNN. In supervised learning, loss functions are calculated using mean square error for goal directions and cross empty for cross entropy for empty spaces. However, as you can see here in these pictures, sometimes visually similar images have different empty spaces. So for this challenge, we apply deep metric learning to the CNN and introduce an additional loss function, which is center loss. This is because the centers is able to improve the compactness of the feature vector distributions within the same class. So we use this total loss function, including center loss, as you can see here, for supervised learning. And after classification, empty space images are generated. Let me show you an example here. Now in the RGB image, only the light space is empty. So the classified result should be 0, 1. So in this case, first, the pixel values within and above the bounding box of the detected object are set to black. Then also, because both the spaces are already detected, the pixel values within and the left non-empty space are also set to black. In doing so, finally, we can see the light empty space is highlighted in red. So this generated empty space image is then used as the input to the subsequent motion planner. Okay, in this experiment, the robot attempts to store objects into empty spaces in the shelf using the proposed empty space classifier and motion planner. And for this task, the robot next stage equipped with a Microsoft Azure Kinect DK is used. And this robot stores objects onto the upper shelf without partitions. Instead, a single object is placed in the shelf. And for string motion instructions, this object is placed at the position A, B, C, D, and E. So this environment with the placed object is referred to as A, B, C, D, and E. So here, let me show you an example. This picture shows environment A because this object is placed at the position A. And in this environment, in consideration of the size of the robot hand, only the right side of the object is empty. In order to verify the effectiveness of using deep metric learning, we compare the classification performance using these two types of loss functions. Moreover, segmentation images and empty space images are used as the inputs to the respective motion planners. Here, this table shows the classification results when the position of the placed object was varied by 10 millimeters between environments A and B, and also between environments D and E. First off, regardless of the loss functions, both the classifier identified the correct empty spaces in these instructed environments A, B, D, and E. However, the classifier trained with deep metric learning sometimes misclassified the empty spaces, as you can see here. On the other hand, the classifier trained with deep metric learning successfully identified the correct empty spaces, even if the object was a little bit shifted. Now let me show you the feature vectors which are extracted from images corresponding to two different empty space classes, namely 1, 0, and 0, 1. For visualization, the original 500 dimensional vectors were compressed into a two-dimensional space. So first, in the left-hand side, we can see that the distributions were broader. But on the other hand, in the right, the distributions were more compact. So this result indicated that deep metric learning enabled the classifier to extract distinct uh, feature vectors even from these visually similar images. That's why this classifier was able to connect identify the correct empty spaces in all the environments. Okay, now using the result from the classifier, the object based on the motion planners first attempts to store objects into the known environments from A to E. And if the robot completes all the trials, it then stores objects in unknown environments from F to I, where no storing motions were instructed. So first, with the segmentation image inputs, unfortunately, the robot failed to store the objects in many environments. On the other hand, with the empty space image inputs, the robot succeeded in storing the objects in all the known environments. Moreover, because of the improved generalization capability, it also succeeded in storing objects in these unknown environments. So here, please have a look at these videos. As you can see here, with the segmentation image inputs, we can see that the objects grasped by the left hand collided with the placed objects. On the other hand, with the empty space image inputs, the robot was able to store the objects into the correct empty spaces, right? So to discuss these results, we further examined the difference between the segmentation and empty space image inputs in environment A and B. For these visually similar image inputs, we can see that also the segmentation images were very similar. So the empty space, the motion planner was not able to associate with these collect storing motions with these different empty spaces. On the other hand, in the empty space images, we can see that uh, we can see the different empty spaces. So the motion planner was able to associate the collect storing motions with these different empty spaces. Okay, in conclusions, focusing on visual spatial perception, we presented a CNN-based approach to object storing motion planning, and deep metric learning was applied to the empty space classifier, and empty space images were then used and generated and used as inputs to the motion planner. Finally, the robot was able to store the objects into the correct empty spaces, not only in known environments, but also in these unknown environments because of the improved generalization capability. Okay, that's it. Thank you for watching this movie.